So for
So
the next three
for the next three
lectures, we are
lectures, we are going
cover
to cover
everything that you need to know about medical image segmentation with deep learning. So we'll try to systematically build from the year 2015 all the way through 2023. So try to cover what has happened over the past 8 years, right when deep learning took off, and what is the current state of the art. So what will you learn by the end of these three lectures? So as I said, we'll systematically develop segmentation architectures and loss functions, and then try to understand and navigate the segmentation literature. I'll try to create a mind map of the different domains of how the field is structured, so that you can what you want and what you're interested in, and dive later on. So think of these three lectures as all the resources and tools and papers that you really need to know so that you can build up your own architectures, functions, and apply these tools and create your own methods and algorithms for the problems that you're interested in, right? So just to tell you, like, it's very daunting, to be honest, to like go through the deep learning literature these days. So just to give you an idea, this year alone, right now we are the main conference, which is MICAI for biomedical image analysis. It's going on, and there were like 2,300 submissions. Out of that, 730 papers got accepted, and there are a total of 900 papers in that conference. So imagine, like, how do you navigate out of these 900 papers? 450 might be like segmentation papers, and it's really tough to organize these into different domains and to have a clear picture of where to begin with. So as you go through these slides, just try to think of how systematically things were developed and improved over the years, right? So that you know which component to tackle on for your own research problem. Also, feel free to interrupt at any time. If you don't ask questions, I'll try to ask questions. Sorry. So just to understand the plan for the next 3 days. So today we'll try to cover the state of the art lectures, the state of, and try to understand goes into architectures, how different functions are designed for problems. That's like, and after that we'll try to understand how to improve these networks, weakly supervised, self-supervised learning, in particular what representation learning means. Then I'll try to say a few things about generative modeling and image synthesis that is used for domain adaptation, generalization. The next time we'll go a bit deeper into what domain entanglement meta-learning is. These are again methods to solve the data covariate shift medical images. We'll wrap up day 2 with some of the work that we are doing in the lab, in particular with topology aware and metric constrained architectures. And then try to cover what is happening in the field as particular architectures such as transformers, surface-based parcellations, what uncertainty measures means, diffusion models, and normalizing flows. Yeah, so let's get on with day 1. As we go through these different architectures that I'm going to talk about, just think of how over the years, every architecture had a small tweak in them, and given an architecture choice that was made in a particular paper, what kind of improvement was made from the previous paper. And then also think about what a particular loss function is doing for a particular anatomy of interest in your modality, right? And the third ingredient that we have in any deep learning network is some form of prior, right? This could be in the form of implicit priors or explicit priors, where you're giving extra information to the network about a problem that you already know that you want to solve, right? So it could be, for example, you know that you're trying to segment a long vessel, and you know that vessels have these elongated structures. So can I give some information into the network which explicitly takes account for segmented vessel, like a thin, long structure? Then the second part of designing a deep learning network, you also think about, once you have a network, how could you post-process a segmentation result, right? And also think about what other strategies you use so your network generalizes better to unseen domains, and also to data regimes which you have not about when training a learning model, right? So for example, as you might have done in your assignment work, for T2 images, if you're training a model on T2 weighted images and trying to generalize it to the scan, it might not work directly out of the box. So you might want to incorporate some data augmentation strategies so that a model trained on T2 weighted images would then be able to generalize to the CIS scans, right? Also, these examples, open source data sets are there and what state of the art open source and get started with. So we know that there are three image segment problems in segmentation, where you are only, but you want to label every instance of the foreground object. So for example, on the left, you can see that you are interested in the foreground, which consists of cows, but you want to label cow number 1, cow number 2, and so on. Then the second type of segmentation problem is semantic segmentation, where you are in a label every object in your image. So here you would give sky, grass, cows, and trees a different label. And the third kind of segmentation is the combination of first two, interested in all the different labels in your image, but also in your foreground class, you are interested in every instant of that foreground object, right? So in this particular set of lectures, we are primarily interested in segmentation, interested in the different labels in your medical image. Just to recap, I've already seen this in the two lectures that you have seen for this class. The first is, the two things to notice is that you always have an input image. It goes through a convolutional neural network, which has a bunch of different layers, activation functions, max pooling operations, whatever you have. And then it goes through an softmax output to give you the final predictions, right? One thing to notice over here is that convolution networks, or these convolutional layers, are basically taking an input resolution, and it will give you the same output resolution, right? If it is a H by W image, it will give you a H by W prediction. In particular, in this particular network, you can see that all the convolution layers over here, they have the same structure and the same size, right? So essentially what it is doing is it is processing the entire image at the same resolution. So there are a couple of drawbacks of doing this. First, that the computer power really increases. It's really high because all the layers have the same width and the same length of your filters. So that increases the computational power. Second, is that you really need a lot of different layers to be able to see every part of the image so that you get a perfect output. That is, this particular kind of network doesn't really capture each and every receptive in your image, right? So these are the two different drawbacks. So what people usually do is they have an autoencoder kind of a network, which gives you the final output. So what you're doing over here is you again have the same input and the same output, but at this time, in this autoencoder kind of a setting, you have a bunch of downsampling layers and a bunch of upsampling layers. So it gives you two benefits, and it tries to mitigate the two drawbacks that we talked about. First, since it has different sizes of filters in your convolution blocks, the computational power is reduced than what we had before, because here we all had the same convolution filters here of different sizes. You can get a computational speed up, right? The second is that you need much less number of convolution layers in particular architecture to be able to see the entire image at your training time, right? So the receptive here is much better than what you have with just plain convolution layers, right? And because of these two advantages, all the segmentation pretty much employ auto-encoder kind of architecture, right? Which you have already seen in NN unit from assignment 1. Right? It also has a unit kind of architecture, which is but an autoencoder with skip connections, right? This is why we use it is same as what? Oh yeah, but it has the depth is different, right? So the overall size is different. Right? It's D3 and D2. Yeah. So this also encapsulates information at different resolutions, right? Right. Again, you have already seen that in medical imaging, we usually train the networks in 3D patches because of memory constraints, right? So this is generally a typical architecture. You have your input and output and a bunch of convolution layers. So now I'll cover a series of papers, each introducing an additional element into the architecture. And also subsequently, side by side, I will try to describe different loss functions that have been used. Right? So this might be a bit of recap, or because from phase 3 of the assignment, you might be training any unit, which basically uses a sophisticated version of a unit. So unit, as you know, is the main backbone architecture for every segmentation task these days, right? It has been cited over 70,000 times. Basically, they do this. They have this architecture with skip connections. And right. So you have an input image over here of size h times w. You can have as many channels as you want, right? And your image will be a 3 patch of cubed. And you want a output segmentation map, again, of the same size, right? So that is a task. And the loss function, you can use any of the loss functions that you are already familiar with, such as cross entropy or dice loss, right? Or any surface-based loss. Now, what really goes into this architecture? So as you can see, it has 3 different components, right? The first is this downsampling component, which takes the original and it's on downsampling it. By downsampling, I mean it can either increase or decrease the number of filters, but subsequently the h times w, the image in the width, that keeps on getting smaller, right? The second component is something called the bottleneck features or hidden features. It captures all the information from the image into a latent space, right? Then the third component is the upsampling layer, which brings back upsampling leg of the architecture back your image from this latent space back to its original size of h times w, right? So why do we have these 3 components? And the fourth component, which I also mentioned about, is that the skip. So why do we have each of these components? Okay, so the first component, which is the downsampling leg, what it basically does is it is trying to capture the context in the image as to what the image is trying to convey, right? The second, I'm just giving a high-level overview of intuitively what these things means, right? The second component is the latent feature. So whatever information you extracted so far, it basically compresses all the information into a latent vector, right? And the third component, which stacks up a bunch of upsampling layers, it gives information about where exactly the organ of interest or the anatomy of interest that you're interested in your image is, right? So it gives you some sense of precise look in the image. Okay, so that's the advantage of these three, or the benefits of these three components in your unit. So what exactly happens at each of these layers, right? So let's say we start with this input image, right? It downsamples it from, let's say, 572 by 572 to 128 by 128, right? Or sorry, 280 by 280, right? And 128 is the number of filters. So it's a 280 by 280 image and 128 of those filters. Okay? And then also try to focus on this particular part of the network. So the output coming from here, right, and the output coming from here, both of these outputs are basically concatenated together and then sent through a bunch of other convolution layers to the next stage, right? So all this is doing is basically you have this autoencoder network, and it is concatenating information from the downsampling leg with the corresponding upsampling leg, right? So again, it happens at every stage. Take the corresponding output from the corresponding downsampling leg, and then the current output from the previous upsampling leg, concatenate them together, run them through a convolution block, and then send it to the next stage, right? So by doing so, it is able to capture the context from the previous layers and also able to localize where the region of interest is in your image, right? Obviously, you need to do some cropping to make sure that the sizes match so that you can concatenate. But these days, you really don't do cropping anymore. There is strided convolutions which take care of all the image dimensions, right? So all you need to know is that how this autoencoder with skip connections is able to capture context and localize the region of interest. Yeah. Yeah, after passing through convolution. Yeah. Any other questions? So yeah, some of the results from this. So this was all done in 2D. When it was first proposed, it was done on 2D slices. And this is by today's standard an outdated paper, but you can see that at that time, the second best model for the segmentation task, which was a non-deep learning model, I think it was 83% dice. And then this deep learning model gave almost a 10% improvement, right? And that's when everybody moved on to deep learning. And same goes with the other task, right? Well, here we see 30% increase in dice. And then there are some other examples of where original unit architecture was applied. So these are 3D cells and neurites segmented in 3-dimensional space. And other also at very micro scale segmentation of gene expressions and microglial cells. And this again you have seen in any unit. If you have started training, have you started training in phase 3? Okay, so okay. You will start training any unit in phase 3, and then all this knowledge will be useful. Okay, so we saw the first architecture, right? So this is how the rest of the lecture is going to look like. Now you know that there is something called an autoencoder with skip connections, aka unit. Now, how can I improve this architecture, and how can I be smart about choosing loss functions so that my particular anatomy of interest is better segmented, right? So one of the first things that was incorporated into this unit architecture was something called a ResNet module. Now, ResNet module was obviously it was more in the computer vision field, or like discovered in the computer vision field for classification task, but people have been using these ResNet modules for segmentation tasks as well, right? So the question that you would ask after training a unit is that, hey, if I want to just increase my accuracy, probably the best solution is to stack more layers and put a bunch of more convolution layers and improve the accuracy, right? Turns out that's not true, because as you stack on top your higher layers and actually get your accuracy, or your accuracy saturates. So that is called a degradation problem, right? That if you stack more and you're stagnant, right? Architecture choices. So instead of you improve the accuracy in different ways. So what is a ResNet module? It is again an autoencoder kind of an architecture, kind of like skip connections, but skip connections used very frequently. Think of it like that. So you have a bunch of different layers. These are just convolution layers. Every block here represents a different set of convolution with, let's say, max pooling and activation function. And what they basically do is they incorporate this particular part called a ResNet module, right? And then obviously you have your same input image and your output, be it a classification task or a segmentation task. So how does this particular block, let me zoom this a bit. How does this look like? So if you look at the left, right, on the left, you can see that you have this output coming from a previous layer. Let's call this output X. So this could be anything coming from this arrow, right? So your output coming from a previous layer, you pass that output through a bunch of convolution layers with activation functions and max pooling operations or what have you, right? So you have this output X from a previous layer, pass this through a small convolution block. Let's call that convolution block f of X, right? And this is the output that you got, right? F of X. That's it. Now what you do is, the output that you got, you just add the original input X back to it, right? That's it. So you have an input X, you pass it through a convolution block F, you get F of X. Now I'm just adding that X component back to that F of X output, right? So it's basically take an input, pass through a convolution block to get F of X, and now add the input back to this F of X, right? So what it does is basically taking the information from a previous layer and adding it to the output from the current layer. Right? What it basically does is it just adds more context as your network depth keeps on increasing, right? So that the network doesn't forget what it was learning from the previous layer. So if you stack 100 layers, let's say, this particular way of doing it doesn't, it forces the network to be able to keep track of what is happening in the previous layers, right? And this helps in the degradation problem that I talked about. The stacking layers usually cause a saturation accuracy, though in this way, it helps to overcome that. And the small piece is just called a ResNet module. Right? So you can basically stack these ResNet modules on top of each other to get a segmentation network. Right? Does this make sense? How a small addition of the simple idea can improve the accuracy of the segmentation network without compromising the computational power. Any questions so far? Okay, couple of things, a little segue here. Now that you have seen two different kinds of architectures, what about the loss function, right? So let me try to break this slide down. So loss functions can be divided into two different kinds of arenas. One is the fitting loss. The other is regularization loss. So fitting loss could be something based on your volume of the segmentation. So something like cross entropy loss, which I guess you already know about, or a dice loss, right, which is in phase 2 to compute reliability. So it computes an intersection of a union, the output and the true bill, right? So these are based on the volume of the segmentation, right? The second kind of loss also that you can have in the fitting loss arena is you have some kind of surface-based loss. So something like Hall distance, where you instead of computing the volume, you compute the distances between predicted output and your actual output. So you see how far they are at the boundary, right? So that's based on and of a segmentation. The second kind of losses is fall in the category of regularization loss, where once you have a segmentation, you also want to incorporate additional information so that your network either does not overfit or underfit, and also give extra information to the network of the topology or the shape or the size of your output, right? So we'll talk about this particular set of losses in lecture 2, where I'll go in depth about how to get a segmentation which is both geometrically correct and topologically correct. So again, another way to think about this process is that you have all your losses over here, your dice-based losses, which are like intersection over union kind of losses, and then your boundary-based or surface-based losses on the third side. And then you can mix and match these losses to get your final loss function. So we will see these both the slides. So a couple of losses that I want to just show you the formula for. So the dice loss and the cross entropy loss. So just to focus attention, this cross entropy, the weighted cross entropy loss. So what it basically does is for every pixel location or voxel location in an image, for every label going through 1 through k, your k classes, you basically get a dot product between the log of your predicted output, right, times the actual value of that particular pixel, right? So, and then you sum them up across all the labels and your entire image. So it's just, think of it like your actual labels times the log of the probability of your predictions. And then you sum them up over your image domain and you get a single value through which you can compute the backpropagation. Another loss, which is the most common loss used, the dice loss. As you can see, it's the intersection of your actual prediction and your actual ground truth labels and your predictions, right, over the summation of ground truth labels and your predictions. So this is just written in formula where the one with y is your actual ground truth label for that particular pixel, and y cap is your predicted output. And then you sum them over all the labels through your entire image domain. And then you divide it by the number of pixels in your domain. And the second kind of loss that I was talking about was this notion of Hausdorff loss, where let's say the blue and the green curves represent, blue represents your predicted output, and green represents your actual ground truth, and you're trying to compute how close or how far apart these two predictions, the prediction is from the ground truth. Let's not get into the math of this thing. But yeah, so if you have a 3D structure, you can just compute voxel-wise distance between these two structures, right? And obviously, we want lower distance between the two structures. Cool. Just a segue. So we have seen NN unit. Well, you have seen NN unit in assignment 1. So it basically combines unit with the ResNet modules, and it has a lot of architectural and a lot of post-processing and pre-processing, data augmentation, and different kinds of loss functions, which it takes care of. And that really makes it the state-of-the-art architecture for image segmentation for medical imaging. So this is from the paper, NN unit, where they segment a plethora of different anatomies spanning across different modalities. And they are top on the leaderboard for almost every biomedical segmentation challenge. Right? And then they have these rule-based parameters where they try to pre-process your input image, make sure that everything is in the same space. They go through intense data augmentation. They have a lot of variety of architectures in their portfolio, which they mix and match. And again, they have a lot of loss functions whose different combination you can try and set up to get the best possible output for your segmentation. Right. So as I was saying, a lot of design choices that they have made, which you can tweak around for the phase 3 of your assignment to get really the most out of this architecture, this code repo. So you can try playing around with different loss functions. They go beyond dice and cross entropy. They have, I think, like 10, 15 different losses, which you can try. Architectures, a lot of different variants of the architectures where you can play around with normalization of the different layers, the activations of the different layers, the different kind of unit architectures, constraining for topology, and constraining for different ResNet modules, attention mechanism, etc. And then they have a lot of post-processing step as well to make sure that different architectures and loss functions and different design choices really give you the best possible output segmentation. So one thing to notice over here is that they are like what we realized when we were training in a unit for our research is that data augmentation really helps. And that was the one main thing that was giving us boost in performance across different kinds of images spanning different modalities and MRI acquisition protocols. So this particular paper, they go through like simple rotation, scaling, addition or removal of Gaussian noise or different kinds of noises, gamma correction, brightness and contrast. I would recommend like try to think of more smarter ways of coming up for data augmentation strategies because this can really boost your performance than anything else in this particular repo. I'll talk about a couple of different ways of doing data augmentation implicitly. So they do explicitly like have functions to rotate the image, but are there other ways of doing data augmentation apart from just rotating or scaling your images? So I'll cover that in a bit. Some more examples of NN unit which we have used in a lab is basically train on this high quality data of ultrasound heart images. This is the left ventricle in ultrasound. This is the left ventricle cavity. These are the anterior and posterior. And what we observed was that just with small amount of training data and heavy data augmentation, we were able to generalize it across a lot of different sequences and images. So these are some 3D examples where you can really see that the network is able to understand the differences in these regions where there are hardly any boundaries. And again, data augmentation is the real key here. So now some self-promotion time, uh, so basically this is what you're doing in assignment 1, right? Trying to use this postmortem ex vivo data at 7T using the 2 sequences and trying to segment the gray matter from the rest of the image, right? So in the lab, we have done this at T2 weighted sequence at 7T and also imaged at 300 microns, which is like isotropic 0.3 mm. And also we did this at T2 star flash at 160 microns, which is 0.16 mm isotropic, right? So what we do is once we have the tissue specimens spanning across Alzheimer's disease, we image them at high resolution, which you already know, and then try to segment different structures in the brain. I guess for your assignment, you're only doing gray matter and white matter. I'll try to show you how we came up with methods to using NA unit and other architectures to segment other structures in these images as well. So on our data set of around 140 specimens, we were able to segment, train the models using manual segmentations and then using different variants of NA unit to segment the different structures in the brain. So in particular, I'll tell you about how we segmented cortex, the white matter hyperintensities, shown here in pink, and then the 4 subcortical structures over here, thalamus, putamen, caudate, and globus pallidus. So we collected some manual segmentations on 4 to 7, around 7 or 8 brain specimens and trained around 10 different variants of different architectures within the NA unit template. And what we found was that, again, data augmentation really helped in giving us a good performance boost. So this is what we ended up getting. These nice looking segmentations just trained on a few subjects. So I'm just trying to tell you the power of NA unit. And then a model which was trained on T2 weighted images. It also generalized well to T2 star flash sequences. So you can really appreciate the high resolution nature of these images. You can really see different structures of the brain in detail. Right? Okay. So if you want to boost in your phase 3 of your assignment and also your extra credit, I would highly recommend playing around with different architectures in NA unit and different loss combinations of loss functions and try to come up with smarter ways of doing data augmentation. These 3 things will give you a nice performance boost. So one thing, this is a bit segue, but we will come back to this in lecture 2. So one thing that you notice in these images, if you zoom in, gray matter, white matter segmentation, gray matter segmentation from the rest of the image, right? But what you really notice if you zoom here is that there are regions of the brain which should be separated but are not separated. And this is because we have not accounted for imposing topology in the brain, right? So as I was mentioning, telling the network that, hey, this part of the brain should be labeled as the CSF, but it is being labeled as the gray matter, right? You see over here, the small region is really hard for the network to understand whether this is background or whether this is a gray matter, right? Or for example, over here, this is a bridged sulcus, right? This is a sulcus, and then this part is bridged. But in reality, this should be 2 separate sulci, right? So there should be a line going on which tells the network that this is the background, well, it as gray matter, right? That's really thin line over here. Right? So there are ways to incorporate this within the network, definition of topology inside the network, or you can also impose this topology correction step after you run your network and use it as a post-processing step. Right? So I just want to show you a couple of one how we were able to solve this problem, but how we did it, that's for lecture 2. So again, if you see this particular MRI where you have gray matter segmentations, here you can see in this region and this region that the background is being marked with this gray matter label, but in reality, it should be given a background labels, right? And after a topology correction step, we were able to separate the foreground from the background, and this nice looking line you can easily see in these two regions over here when compared to without topology correction. Right? So how do we do it? It's for lecture 2. That's probably the most interesting part of these 3 lectures. It's pretty cool, like think about integrating nice theoretical math into just these complex structures and how to segment or to separate out these 2 regions. So it is called topology, post-hoc topology correction. And we do pretty much the same thing also in a much higher resolution of the medial lobe and 1.4T, trying to separate the same problem of bridge cell at this particular high resolution, right? Again, we take any unit, put some more to be able to correct for this topology. Again, this is for lecture 2. Right. Okay. As I promised, apart from in unit, there's another framework. It's also one of the buzzwords in the field right now. This particular toolbox, it's again based on PyTorch and Python, and you can use this to basically do a lot of image and registration stuff with deep learning. Right. Any questions so far? Okay, so I talked about loss functions for a bit. There are these different kinds of loss functions. I talked about data augmentation for a bit, and the main focus was the network architectures itself, right? So now we'll go back to network architectures and see that from UNIT, we went to ResNet, and then what other architectural changes can we make to even get much more better performance of these architectures, right? So the problem of brain parcellation. So over here, you can see T1 weighted images of a brain, of a human brain. And what you're trying to do over here is to try to parcellate or segment the brain, both the cortical and the subcortical regions into different regions, right? So the famous tool, if you're in the brain imaging community, you'll probably use this tool all the time, called FreeSurfer. So what it does is basically takes a T1 weighted MRI, structural MRI image, and parcellates that into these different kind of, these different 95 regions, right? And this is all done without deep learning, right? So I'll talk about how they did this with deep learning based approaches. And their non-deep learning version is called FreeSurfer, and their deep learning version is called FastSurfer, right? So FreeSurfer based things I'll talk about in lecture 2. For now, we'll talk about what FastSurfer means. So the goal here is to take your input image and segment it into a different levels, right? So another variant of the way that you can train your neural networks is, right now we were training our network in 3D patches, right? So the problem, so we have a big image, let's say of 250 by 250 by 250 voxels, and we put them into patches and we train in on our GPUs, right? And we do that because of the computational power. We are limited by computational resources and memory constraints. Okay, that is fine. But can someone tell me what is the disadvantage of using patch-wise training. Yeah, exactly, right? So patches will only see small structures, and as Mohammed said, it doesn't know all the global structures. So what can we do to improve that? And at the same time, also think about how can we do that, given that we have memory constraints, we are limited by memory constraints on our GPU, right? So what FastSurfer does is, it basically, instead of taking 3D patches, or instead of taking the whole 250 cubed image, it operates on slices. But again, you can say that, okay, one slice, again, you don't see really any context. So what they do is they take, let's say, a bunch of different slices, right? But they take it at the full resolution. So you're seeing the entire image, but you're seeing a chunk of image. So that's like a reasonable midway from patches going through all the way to full image, right? So over here, what they do is they take this coronal slice of T1 weighted structural image, and they take 7, or let's say any odd number, 11 or 13, right? Stack of slices. And then they try to output the 95 labels in that particular image. So they take 7 slices, but they predict the output only for the middle slice, right? So if slice number 5, I want segmentation for slice number 5, my input will be 3 slices before that and 3 slices after that, and also slice number 5. So I have 7 slices, but I'm only predicting my segmentation for that middle slice, right? So this way, it gets context from a bunch of previous slices and a bunch of slices coming after it. So 7 slices here, output is 1 slice or channels, right? And again, you see you have this unit kind of architecture with long skip connections, right? And the other important thing that they do over here is that, or architectural choice that they make, and then they empirically show that it is a better choice. So what we were doing in unit was we had an output from the previous layer, right? And we had an output from this particular block, and we were just concatenating these two layers together, right? So instead of doing that, so this is what they were doing, like output from this layer and output from this layer, concatenate that and have a 6-channel image. What they do is they take the output from here and they take the output from here, but now they run it through a max out operation. What basically it does is that it compares every voxel and the corresponding voxel from the other output, and it says whichever voxel has a higher value, I'll just take that value, right? So if this is a, let's say if this output is 3 by 3 by 3, and this output is 3 by 3 by 3, shown over here, right? It will check each of those 27 voxels, corresponding voxels, and it will choose whatever the higher value is, and it will give that as an output. And instead of outputting 6 channels, it is just outputting 3 channels. Right? Yeah. Yeah, so it's just like, let's say I have 300 slices, right? 300 coronal slices. So I'll just feed my entire image and put in my Python code that this input will sequentially take. So every slice would eventually be a middle slice, right? Starting with leaving first 3 and the last 3 slices, so that. You put some other slice from, think of it round robin, and then you can take, so the first slide, you can take the last 6 slices from the top, from the bottom of the stack, right? So, or you can reflect your image around the borders. Who cares about borders anyway? So, yeah. So there are multiple ways to do it. Normally, they just reflect it, or you can also just concatenate that, make it like just copy the values on the borders again, reflect that, take it from behind. Yeah. Because anyway, at the borders, these structures are really small. So it's already a background over there. Yeah. Any other question? So it is a tensor with them. Oh, sorry, what was the question? Like, oh yeah. So think of it as like, when I say channel here, think of it as 7 can be the depth of the image, right? So we have 64, 64, 64 when we are training, let's say patchwise. So think of this as 7 times 64 times 64. And the channel would be 1. Does it make sense? So if you put in PyTorch, but that size times channel would be 1 in this case, and depth would be 7, height and width would be 128. And I create the tensor. Cool. Right. So that was another architecture choice, which in their case, it worked better. Now let's think about post-processing, another step which I told you about to think about when designing these deep learning architectures, right? So we were just talking about how you can do it in coronal direction, right? But nothing stops us from doing the same thing for the same set of images from the other 2 directions, that is axial and sagittal, right? So I can train 3 different deep learning models here, one for coronal, one for axial, and one for sagittal. And then this way I would have, for every voxel in my image, I would have 3 different predictions, one coming from the coronal CNN model, one coming from axial, and one coming from sagittal CNN model, right? And then I can just do either a weighted average to get the final output of what that particular voxel label should be, or I could do a majority voting between these 3 networks, or whatever operation you want, right? So it's just a way to the final. So this way, you can also think about that affect the border images as well, because it will seem in one of the 3 directions. Okay. So this was the architecture we talked about. Now, as I promised, there was a 5th way to look at these architectures and think about how to improve the accuracy, was trying to add additional information from the world, or which you already know about your problem statement, right? For example, as I spoke about it earlier, that if I want to segment a long structure, such as a vessel, which has a lot of bifurcations, I can impose some set of metrical constraints in the network itself, so that it knows that, hey, I'm trying to segment a long structure instead of something like a spleen or a liver, right? So continuing with this brain example, so we know that there's a left hemisphere, there's a right hemisphere, but over here, so there is left and then there is right. And you know that, well, we know what is left and right, but the network, for network, it's the same thing, right? It doesn't have any notion of what is the left hemisphere and what is the right hemisphere, right? And if I want to label my every part, every subcortical region or every region in the brain in my image as either coming from left hemisphere or from the right hemisphere, I need to put some explicit constraints or explicit knowledge into my network so that it knows this particular brain hemisphere is either left or is either right, right? So how can I do that? So again, I'll go back to my network architecture and try to incorporate some information so that it knows that this cortex or this particular part of the brain, this frontal region is coming from left or right hemisphere and vice versa, right? So one way to do that is it comes from the same group of co-authors, is that you can try to put a coordinate system to every voxel in your MRI, brain MRI image, right? I have a 3D image, and I know that these set of voxels are coming from left hemisphere, and these set of voxels are coming from right hemisphere. So at every voxel, I can put a coordinate, right? And I can try to predict this coordinate also in my final output, and thereby I can put some kind of information about what exact label to give to this particular part of the brain, right? So what they do is they try to put this implicit prior of coordinates through something called eigenfunctions, right? So we will try to segue a bit and first learn what eigenfunction, and then how can we just put that information into the network as an additional layer so that it knows what the coordinate is for that particular voxel, right? So we'll try to break this down. So let's say you have your function f, which in our case is some image in Euclidean plane, right? And from earlier this semester, you know that you can compute gradients in your image in x, y, and z direction, right? And nothing stops you from computing higher order derivatives, partial derivatives, right? So this basically is your image I, compute the second order gradient in the x direction, and then compute the second order derivative in the y direction, right? And you just add these two things up. And that gives you a quantity which you might have heard in physics called the Laplacian, right? So this is the Laplacian operator, summation of all the second order partial derivatives, right? Another way to think of it is as the divergence of the gradient, right? Gradient is dou x, dou y. Divergence is taking this derivative of it and adding them together, right? So you know how to do this in image plane, right? It's just 2 lines of code. And then nothing stops you to take this idea and apply to that, to surfaces and to meshes, right? So you can think of your images, your final segmentation of your brain, instead of thinking them as volumetric segmentations, you can convert that into a mesh, again by 1 line of code, and apply this Laplacian function to every triangulated surface on that mesh, and then that's it. That's called the Laplace-Beltrami operator. So we have a Laplacian in the image Euclidean space, and when you apply this operator to the surfaces, to the meshes, you just call it a Laplace-Beltrami operator, right? So going back to this, I said that now we have these labels, right? But we want to compute, to give them a way of incorporating this coordinate system within the network as additional layer. So what they do is they take this output segmentation. Again, everything is happening in the network. Somewhere in the network, you get these segmentations, and which you can compute, which you can convert into meshes, again, somewhere in the network. And once you have those segmentations, right, you can compute the Laplacian on that, right? And once you compute the Laplacian, you can decompose the Laplacian into its eigenvalues and eigenfunctions, or eigenvalues and eigenvectors. Eigenvectors in mesh domain is called eigenfunctions, right? So I'm segmenting my network. I just convert that into a mesh. Sorry, I'm segmenting my brain. I convert that into a mesh. I compute this Laplace-Beltrami operator on it, which gives me a set of eigenfunctions or eigenvectors. And these eigenvectors or eigenfunctions basically tell you about, it gives you a sense of coordinates for that particular brain structure, right? And then you can just stack that as another layer, or you can make it as part of the network and back propagate through the entire thing. So it's just one way of trying to give some information about where my particular label is coming from, left or right hemisphere of the brain. If you don't understand this, doesn't matter. But just one line is that there are external ways of putting information into the network, such as this fancy math, so that you know, or you try to extract some particular information from your brain, from your images. And then earlier, it's not used these days anymore, but once you have these segmentations from your output, people used to, have you studied Markov random fields in this class? So once you get these segmentations from your neural networks, they often, this was like 2014, 2015, they didn't look quite well. So they just ran the segmentations through a conditional random field or a Markov random field to smooth out the labels and get a better segmentation. So this is, again, what people used to do for post-processing. Okay, so far we have seen network architectures, loss functions, data augmentation, pre-processing, post-processing, trying to incorporate different priors into the network, right? So by now you should have a good idea of what it takes to build a deep learning system to win a challenge or to get really nice, accurate segmentations or to get extra credit in your course, right? This is, any questions? Okay. One last thing, one last addition to the network, which I feel is very important these days to understand network. So again, this unit architecture, we have autoencoders, we have connections, and we do something here. We add something extra over here, right? Just like we did in that neuroanatomy definition, we had that max out operation, right? So these authors, they try to put an attention module. So what does, imagine you are trying to segment an image which consists of a lot of different parts, let's say your abdomen, right? In a CT image. And your abdomen consists of a lot of different organs, and you want one model which segments all these different structures, like your spleen, pancreas, livers, heart, intestines, right? And for a single model to try to come up with ways to be able to segment all these structures, it might get tough. So there was this thing called attention mechanisms, which tells the network that for a particular label, you should be focusing in this particular part of the anatomy or of the image, so that you are able to segment your particular region of interest. So these attention mechanisms, basically, as the name suggests, it tells where to attend to in your particular image. So on those particular target structures of different shapes and sizes, right? So there are ways you can come up with these attention modules. We'll try to look at one of the ways. So keep in mind, for the next slide, you have this input number 1 coming from a previous layer, input number 2 coming from layer, yeah, and two outputs together to get an attention mechanism, right? So what it basically does is it takes that input 1 and that input 2. It basically adds these two things together, a bunch of different activation functions. And then the output of these two additions is here, denoted by alpha. And one of the outputs coming from the bottom layer, it just multiplies by that particular output, right? So what it is trying to do essentially is it is trying to take a dot product. So this dot product, it is trying to take a dot product between two different vectors, right? And we know that dot product basically determines the similarity of two different vectors, right? So this is a very like simplistic view of attentions. It basically tries to compute the similarity of two different things, and somehow they claim that this will better attend to the particular region of interest, right? So going back to the slide, you have that input and your output, sorry, your input number 1 and input number 2. It goes through this whole attention mechanism, and it gives you some output, right, at the end, this output. And you just concatenate that again, right? So what it is doing is, for the layer, it is taking information from the previous layer, but in a smart way, it is trying to compute the similarity of every voxel between these two layers and trying to see which particular voxel to give more weight to than other voxels, right? Because a summary, there is more math behind this. Yeah, and then you can see from left to right, these are two different viewing planes on the bottom. So from left to right, images are as the network is time. So over here, you can see these are attention coefficients. So when the network first starts training, you can see that it's trying to see where in the image and doesn't have an idea of where to look at to segment the different structures in the image. And over time, as it trains, you can see that it is really able to localize into the regions that it is trying to segment, right? So in this case, it's kidney, pancreas, and spleen. Right, and then they click, if you see on the left, unit output, where it misses this particular structure, attention, it is able to rectify this. But again, I mean, networks, they are, I mean, if you run on your images, they might not work. This is just, this thing didn't work for my ex vivo project at all. Vanilla, any unit was way better than attention. Yeah, and then you get nice results, and then you can publish a paper. Yep. Just trying to think. Okay, one last thing, and then I'll give some introduction for what we are going to do in lecture 2. And then I told you one way of computing attention mechanisms was those dot products. And now you can be really smart about how to compute these attentions, or how to recalibrate to get the maximum information out from feature channels. So just to give you an example, if you don't get it from this 2 sentences, fine. So suppose you have this block of output with height, width, and channels. This is somewhere in your network, right? An output. So what you can try to do is you can try to compress and expand your information in different directions, so that the network tries to see information in one particular area and then doesn't focus on the other particular area, which you're not interested in. So this is something called spatial squeeze and channel excitation. So as the name suggests, we are trying to compress the information from a spatial height and width into a single number, and we will increase the number of channels for the same, right? So what it does is that for this first slice, right, if these are C slices, so I just take the first slice and I just add all the numbers in my first slice, and then I keep on doing that for all the slices. So I'll have 3 different values at the end of the day. So this is what it basically means. I have squeezed all the information of that spatial h times w into a one number, but then I've retained the information along all the channels, right? So at the end of the day, I get this one single vector, right? And then you can do fancy things and multiply this output from the original output and get something like this. And then you can do the other way around as well. Squeeze the channels, expand the h times w to see something like this. So you can see the difference. Right now, this particular network, it is seeing all the information across the channels. And then this particular network or architecture choice is seeing all the information along the spatial dimension, right? And then you can mix everything together to get fancy stuff, right? And then finally, what we have learned so far is coming together in this particular architecture called anatomy net, where you have your unit architecture, you have your skip connections, you have this residual block within every each of these blocks, and then somewhere over there you also have your attention mechanism, right? So you can like really plug and play all these networks, put components together to get better accuracy. Okay. So again, this is, I guess, for lecture 3. So I was talking about how, okay, so now we are done with all the network architectures that you have to see, the different kinds of loss functions, the basic loss functions. And now we can, like, for the rest part of, for the 2 lectures, what we'll be doing is we'll try to see different paradigms in the segmentation literature, right? What is meant by representation learning, what is domain generalization, domain adaptation, then what are transformers. So these are different paradigms that you can use to improve your segmentation results under different circumstances of having a very heterogeneous data set with mixed MRI sequences with low resolution, high resolution images, etc. So a couple of things before going on to the next topic, which I'll keep for next class. So right now, all of the stuff that we were talking about was in volumetric space, right? And I briefly touched upon that. You can compute all this stuff also in mesh representation by converting your voxel grids into surfaces and then doing all your analysis in surfaces using graph convolution networks. So I just wanted to show how these things are done. So here, the cortical surface that you had from before, right? The white matter surface and the gray matter surface. I represent this as a mesh or a surface, and then pass this through a bunch of graph convolution networks to get some kind of final output, which does the segmentation in this mesh space, right? We'll not go into this, but I'm just telling you that this is out there. And then you can compute from your input output, not only segmentations of the different organs, but you can also get cortical thickness, your curvature estimates, just directly by giving your input segmentation and getting these output values that you're interested in. Okay, I have 10 minutes, and good thing is this topic will only take 10 minutes to finish in 7 minutes. Okay, so one last thing to notice is that I kept on stressing about the point that these networks really work well if you do clever data augmentation, right? Because at the end of the day, you're limited by the examples that you have, and you want to make sure your network actually performs in the real world, which it has not seen examples from before, right? The other thing is, can someone tell me what is the real reason why we do data augmentation apart from getting segmentation accuracy boost? Like, why do you want to rotate your image, put Gaussian blurring, scale your image while training networks? Exactly, right? So you want to make sure your network is generalizable to other domains, right? And the other thing is that convolution networks are not invariant and equivariant by design. So you have to impose that structure in the network itself. Is to do that is data augmentation. A good theory here, what is meant by invariance and equivariance. So I just said that these two things are not guaranteed by a network architecture. And that is why we do data augmentation. So for example, there are two concepts, invariance and equivariance, and really important concepts. Like if you don't know this, then it's hard to make to get a boost in accuracy. Like why we make sure that we come up with smart ways so that our network is able to generalize to other domains. So invariance and equivariance. So you want your network to be invariant and equivariant, but by default, convolution networks are not that way. What is invariance? So you have a function f of g of x, and you want to make sure that it is equals to f of. What does that mean in the right? So suppose you have this input cat, right, x, and you want to detect this cat. You want to label it as 1 if it is a cat, otherwise 0, right? And your neural network here is represented by f. So f of x will be 1 if it's a cat, otherwise 0, right? Now, I shift this image, right? The cat image somewhere else in my image, right? And so basically what I do is, to my input cat x, I apply a function of shifting, which I denote by g or s, right? So I apply g to my function, to my input image x, which shifts this cat. And now I apply my neural network f to this shifted input, right? And I want my neural network to be able to still say that even in this shifted image, somewhere in the image, there is still a cat, right? So that is what is meant by invariance, that f of x is equal to f of g of x, right? You are able to detect the cat even if it's shifted somewhere in the image, right? So that is invariance. Now, what is equivariance? Again, f of g of x should be g of f of x. So there is a g here, which wasn't here. If you put a g here, that is equivalent. So what it basically means is, suppose I have my cat was somewhere over here, let's say. I shift it to this place, and I run my neural network f to segment this image. So this is represented by f of g of x, right? And now be equal to first segmenting the image and then shifting the image, right? So it should not matter whether I first shift the image and then segment it, or first segment the image and then shift it. Both the output should be the same. So that is what is called equivariance, right? So these are the reasons why we do data augmentation, so that the network is able to see all different kinds of possibilities of your input data, right? Rotated version, shifted version, scaled version, noisier version, so that it is able to take care of all these different things, and then able to give you a better performance. And yeah, so these are the reasons why we do data augmentation. There are, apart from just doing vanilla data augmentation, there's a whole field of something called group equivalent neural networks, which is a whole subfield in machine learning, deep learning, which again, I'm not gonna go into, but just that just vanilla data augmentation will not help. If you're working with challenging data sets, you have to really think about how to put these constraints of invariance within the network itself, within the network architectures, right? And this is the field based on group theory of how you can build architectures so that you can take care of that invariance and equivariance problem. Yeah, I think and since it's time. Cool. So I think next time we will mostly talk about domain adaptation and generalization, and specifically depth about incorporating topology and geometry. Thanks.